All right, today we're jumping into a really fascinating paper called the Universal Reasoning Model. It gets right to the heart of a major puzzle in AI right now. Why are these small, recurrent models suddenly wiping the floor with massive LLMs when it comes to pure reasoning? So let's break down how they investigated this, the super innovative model they built, and what it all means for AI design going forward.
Okay, so this is it. This is the core enigma that the paper takes head-on. For years, we've all been operating under the assumption that bigger is better, right? Scaling laws, more parameters, you know the drill. But for these really tricky, abstract reasoning problems, that whole idea is getting flipped on its head. So the real question is, what's actually going on under the hood? What's the fundamental mechanism here?
So where does this puzzle even come from? Well, it's all about the frankly incredible success of models that are based on the Universal Transformer architecture. We're talking about models that are orders of magnitude smaller, trained from scratch, and yet they're crushing benchmarks like ArcAGI. They're leaving some of the most powerful pre-trained LLMs in the dust. And this isn't just a one-off thing, it's a real pattern, and it demands a solid explanation.
To get to the bottom of this, the authors basically put on their detective hats. They started by taking apart previous models like HRM and TRM, which were also based on universal transformers. They really wanted to find the true source of their reasoning power, and in doing so, they ended up challenging some pretty common assumptions.
You know, the prevailing wisdom in the field was that the success of these models came from really complex high-level design choices, things like multi-timescale recurrence or other fancy elaborate modules. The community pretty much credited these sophisticated architectural tricks for the big performance jumps. But as it turns out, that might not be the whole story.
Now this is where it gets really interesting. Just look at the raw data from the paper. On the one hand, you've got a universal transformer with just 4x the base parameters hitting a 40% pass rate. On the other, a standard vanilla transformer beefed up to 32x the parameters and the same flops only gets to 23.75%. I mean, that's not a small difference. It's a huge leap in efficiency, and it's a massive clue that how you compute might be way more important than how much you compute.
And that leads us right to the author's central finding stated plain as day. The secret sauce isn't in bolting on more complex modules. Nope. It's baked into the very core of the universal transformer itself, that recurrent inductive bias you get from sharing parameters across depth and the powerful nonlinear components that allow for this kind of iterative thinking.
So what do you do with an insight like that? Well, you don't just write a paper analyzing it. You build a new model from the ground up, and that's exactly what they did. This is where they introduced the Universal Reasoning Model, or URM, which is specifically engineered to double down on those core principles of recurrence and nonlinearity. The URM really boils down to two key upgrades over a standard universal transformer. First up, they created a new module they call conv-swiglu, which is all about boosting the model's nonlinear capacity. And second, they used a clever training strategy called truncated backpropagation through loops, TBPTL for short, to keep the optimization stable over lots and lots of recurrent steps. Let's dig into each of these.
Okay, so the key thing to get about conv-swiglu is that it's a tweak to the feed-forward network, not the attention block. By slipping in a simple depth-wise 1D convolution with a tiny kernel size of 2, it lets adjacent tokens interact right inside the gating mechanism. This seriously enhances channel mixing and just makes the model's nonlinear expressive power that much stronger, which, as the authors found, is absolutely critical.
And you can actually see the difference it makes. It's pretty stark. On the left, that's the attention pattern from a standard universal transformer. Kind of sparse, pretty uniform. But on the right, once you add conv-swiglu to the feed-forward net, the attention matrix becomes way more diverse and structured. It's a perfect visual for how this enhancement is promoting a much richer flow of information inside the model.
Now for the second innovation, TBPTL. This tackles a problem that's, as old as recurrent networks themselves. When you unroll the recurrent model for a bunch of steps, backpropagating through every single one can cause your gradients to become unstable. Noise from the early steps can just wreck the whole optimization process. So TBPTL is this really simple but effective fix. You just don't compute gradients for the first few loops. You treat them as forward only and start the backprop a bit later.
And check this out. The data totally backs up the strategy. This table shows you exactly what happened when they applied TBPTL to an 8-loop URM. You can see the performance actually peaks when the first 2 loops are forward only and the gradients are only computed for the last 6. Trying to backprop through all 8 loops is actually worse, and truncating too much is a complete disaster. It just perfectly nails that sweet spot between learning long-range dependencies and keeping the optimization stable.
Okay, so we have a model built on a really clear hypothesis with 2 very targeted enhancements. But does it actually work? I mean, that's the real test, isn't it?
Let's see the results.
And the answer is a resounding yes. The results are, well, they're definitive. On the ARC AGI-1 benchmark, the URM hits a pass-at-1 score of 53.8%. This is not just some small, incremental improvement. It's a massive leap forward, blowing past the previous state-of-the-art models like TRM and HRM.
And this isn't a fluke on just one benchmark. When you look at the broader picture, the URM just consistently dominates. On the much harder ARCGI2, it scores 16%. That's nearly triple the score of its predecessors. And on Sudoku, it sets a new state-of-the-art at 77.6%. This model is definitely not a one-trick pony. These design principles are clearly robust across different, really complex reasoning domains.
So at this point, it's obvious the URM is a powerhouse. But the paper argues that this is about more than just hitting a new soda on a leaderboard. It really points toward a fundamental shift in how we should be thinking about designing models specifically for reasoning. And if you need one final killer piece of evidence for this new philosophy, just look at this ablation study. It's incredibly revealing. The full model gets over 53%. But if you just weaken the activation function from Swiglu to Silu, performance gets cut almost in half, down to just under 30%. And get this, if you remove the attention softmax, another key nonlinear part, performance completely collapses to 2%. I mean, this is just undeniable proof that strong, rich nonlinear transformations are the absolute bedrock of this model's ability to reason.
So what does this all boil down to? It's really a shift in thinking, a whole new design philosophy. The old way was all about adding architectural complexity, stacking more layers, inventing elaborate new modules, just scaling up the parameter count. The new philosophy, which the URM champions, is all about fundamental enhancement. It's about strengthening that core recurrent inductive bias, boosting the nonlinear power of the parts you already have, and making sure the whole thing can be optimized stably. It's a move away from complexity and back to the fundamentals.
And that leaves us with a pretty big and, I think, provocative final question. This work shows that for a really important class of problems, enhancing core principles is way more effective than just throwing more scale and complexity at it. So that should make all of us take a step back and ask, what other foundational assumptions that we're making in our current models, from LLMs to vision models, are actually ripe for a rethink? And that is the challenge this paper leaves us with.